Hi everyone. Today we're going to study factorial function defined recursively. For each positive integer n, the factorial of n, denoted n with exclamation point, we read this as n factorial, is defined to be the product of all the integers from 1 to n. In symbol, we write like this: n factorial equals n times the quantity n minus 1 times the quantity n minus 2 times up to 3 times 2 times 1. Take note here that by definition, 0 factorial equals 1. Note here that we are multiplying numbers. So, for 0 factorial, we will write the identity element of multiplication, which is 1. Let us show some examples. A while ago, we said that 0 factorial equals 1. 1 factorial equals 1. 2 factorial equals 2 times 1, and the product is 2. 3 factorial equals 3 times 2 times 1, and the final product is 6. 4 factorial equals 4 times 3 times 2 times 1, and this is equal to 24. 5 factorial equals 5 times 4 times 3 times 2 times 1 equals 120. 6 factorial equals 6 times 5 times 4 times 3 times 2 times 1 equals 720. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1 equals 5040. In general, we say 5 factorial equals 5 times 4 times 3 times 2 times 1. We can show that this number 5 is written separately, and we're going to group the numbers from 4 up to 1. But this 4 times 3 times 2 times 1 equals 4 factorial, which means n factorial equals n times the factorial of n minus 1 for each positive integer n. We go now to factorial function defined recursively. We can define the factorial function capital F of n equals n factorial recursively by specifying the initial value of this function, namely capital F of 0 equals 1, and giving a rule for finding capital F of n from capital F of n minus 1. We note a while ago that n factorial equals n times the factorial of n minus 1. Thus, the recursive definition of factorial function capital F of n is number 1, capital F of 0 equals 1. Second, capital F of n equals n times capital F of n minus 1. Example 1. Let capital S be the function such that capital S of n is the sum of the first n positive integers. Give a recursive definition of capital S of n. The initial value of this function may be specified as capital S of 0 equals 0. Take note here that we start the value of n as 0. Also, we are dealing with addition, so it is better to put this is equal to 0 because this is the identity element of addition. Since capital S of n equals n plus the quantity n minus 1 plus the quantity n minus 2 plus and so on plus 3 plus 2 plus 1. Now we show that we separate the first element n plus we group the second element up to the last term. So it becomes like this. And then let us show that this is n plus capital S of n minus 1, which defines the recursive step. It follows that we write like this. Accordingly, capital S may be defined as, number 1, capital S of 0 equals 0. Second, capital S of n equals n plus the S of n minus 1, for n is greater than or equal to 1. Example 2. Let A and B denote positive integers. Suppose a function q is defined recursively as follows. Q of AB equals 0 if A is less than B. Q of A minus B, comma, B, then plus 1 if B is less than or equal to A. Find the value of Q of 2, 3 and Q of 14, 3. Let's begin with Q of 2, 3. Take note that A value here is 2 and the B value is 3. This Q of 2, 3 equals 0 since 2 is less than 3 as defined in our first function here. Now let's go to Q of 14, 3. Again, we note that A is 14 and B is 3. We are now using the second function. Given QAB equals the Q of A minus B, comma, B plus 1 if B is less than or equal to A. We can see here that B is less than A, which is 3 is less than 14. So using our formula here, we write Q11, 3, then plus 1. This 11 here is the difference of 14 and 3. It becomes 11. Then we copy this number 3 in here. Now let us evaluate this Q of 11, 3. We can see that 3 is less than 11. So we follow this formula. We write Q of 8, 3, then plus 1. And outside there is plus 1. So the number 8 here comes when we subtract 11 by 3. Now let us simplify this step. Let's remove the grouping symbol here so we can combine this one and one outside. So we have now this Q of 8, 3, then plus 2. Then let us evaluate this Q of 8, 3. We can see that 3 is less than 8. So again, we follow this formula. So we write here Q of 5, 3, then plus 1. And outside, we copy this plus 2. Remember, the number 5 here comes when we have 8 minus 3. Now let us simplify this step by removing the grouping symbol. And we combine 1 and 2. So we have now this Q 5, 3, then plus 3. Let us now evaluate this Q of 5, 3. We can see that 3 is less than 5. So we apply our formula and we write Q of 2, 3 plus 1. And then we copy this plus 3 outside. Remember that this 2 comes when we have this 5 minus 3. It becomes 2. Now let us simplify this step. When we remove the grouping symbol, we can combine the constant 1 and the constant 3. It becomes 4. Now let us evaluate this q of 2, 3. Take note here that this 3 now is more than 2. We can simplify this by following the first formula. Actually, we have this value from A. So we write 0 plus 4. And we simplify this as 4. These are the answers for Q2, 3, that is 0. And for the Q14, 3, the answer is 4.